All right. So we're talking about work and energy. And so far, we've talked specifically about work done by a single force. When we talk about work done by a force, we are talking about kind of three buckets that have to be fulfilled, if you'll remember, because we're talking about what that force does in moving the object. So when we talk about work done by a force, there's the applied force portion. There's how far the object is moved due to that force or in response to that force. And then there's how much of that force is actually in the direction of motion of the object. Generally, it's this part that tells us whether the force is contributing to the work done or taking away. And from our discussion, we know that positive work means that the energy increased. And negative work means energy is decreasing. So positive means we're adding to it. Negative means we're taking away. This mask is not working. Let's move on to mask number 2 for today. So when calculating work from a single force, I want to remind you that there are those 3 buckets. And this, of course, gives us something that is in Newton meters, which we're going to call a joule. Then we worked or talked about the concept of net work, where we add all the work together. So we're talking about adding all the work done by various forces acting on the object. When we do that, we're adding and subtracting work as it's being done, depending on multiple forces that could act on the object. But what we said in the outcome of that was that network also implies that if something has changed about the object, it would show up in network. Meaning, if network was done, then that's going to equal a change in the energy of the object. At the most holistic level, we're talking about changing the kinetic energy of the object. You can have lots of work done on an object and the network be 0, which means nothing actually changed about the object. Now, we're going to augment this a little bit because although you can do work on an object, you can change its energy and still not change its kinetic energy. We saw that on Friday. You can lift an object, and when you're done, the object still doesn't have any velocity, but now it's higher than it was. So doing that work doesn't tell you if the potential energy changes. It only tells you if the kinetic energy changes. I would probably emphasize that in your notes a bit. Doing that work doesn't tell you if the object's energy changes. It only tells you if its kinetic energy changes. Spencer's trying to get into class. We'll spend a few minutes letting Spencer get into class. But I already marked Spencer absent. Good morning, Spencer.
Good morning.
Glad you're here today. But I marked you absent already.
That's okay.
So you'll do me a favor and at the end of class, remind me to go change my attendance. I would appreciate it because I will forget, okay? Next, I want to also remind us that kinetic energy is written as 1/2 mv squared. And it too would be in joules. If you work out those units, like kilograms, meters squared per second squared, it still works out to be joules. Now, that's kind of what we did all the way up through and including Thursday. And we worked various examples of this, but now we also have something else to add to this. Because on Friday, we talked about potential energy. Potential energy is energy storage, the ability to store the work done and use it at a later time. We only talked about one form of potential energy, and that was gravitational potential energy. Now, in the bigger scheme of things, you need to know that potential energy is any time work is done against a conservative force. I'm going to say that again because it's not something that's part of your vocabulary. Potential energy occurs anytime work is done against a conservative force. There are lots of conservative forces out there. They don't have to be fundamental to be conservative. So there are lots. That means there are lots of different types of potential energies. Although we're only going to talk about 3 or 4, it's important to you to understand that there's lots of different ways that we can store energy. When we talk about potential energy, though, we are talking about a one-to-one correspondence. When we do work against a conservative force, we get a one-to-one correspondence in energy storage, which means for every joule of work we do, we can get that joule back. It's 100% efficient or 100% transfer. For us, we're talking specifically about gravitational potential energy, which kind of has 3 parts. I want you to write it very specifically. This is not really what's in your book or what's in your equation sheet, but it's important that we understand that there is this mention here of H naught that I want you to always consider when asked about gravitational potential energy. The first thing you should do when you're asked to calculate the gravitational potential energy is ask yourself, what is the reference level? What is the reference level? This is something we were talking about right at the close of the day on Friday. The reference level represents the lowest likely place that the object could go. The lowest likely place that the object could go. I was doing that because I wanted you to think about stuff that's, currently in your environment. Most all of you are holding some kind of writing implement, pen or a pencil. Unless you're at home, I don't know what you guys are holding because half your cameras are off, so I have no idea. And just so you know, first period got blasted today because I relied heavily on them to do our sample calculations, and it was clear they were asleep at the switch. So you guys at home, going to lean into you a lot today. And it's all because first period doomed you. You can blame first period at home folks. So the reference level, if you're holding your pen right now, and I asked you, does your pen have any gravitational potential energy? The question you should think about for just a moment is, well, compared to what? If I were to drop my pen right now, is it likely to hit the table? If so, table's the reference level. That's how you should make your comparison. You should calculate the amount of potential energy based on how high it is above the table. But if you were holding your pen above the floor, does that suddenly change anything about the pen? I mean, the pen's no different, but now the pen has the potential to fall a farther distance. So its potential energy has to kind of take into account the new reference level. Even though there's nothing different about the pen, suddenly its potential energy seems different. Now, nothing about the energy actually changed. The truth is, the pen was brought up from the first floor. At some point or another, you did work to bring it up the stairs. Then you had work to take it out of your backpack and put it on the desk. You've been doing work on the pen all day. So the amount of energy the pen has doesn't change, but the reference level can. So when you're asked to calculate the gravitational potential energy, you get to choose the reference level. I want to be very careful here. You get to choose it. You cannot get this answer wrong, but you can make a lot more work for yourself. So generally, what I would encourage you to do is in any problem where you're asked to calculate the gravitational potential energy, find out what the lowest place the object is likely to attain and use that as your reference level for the whole problem. It's not a shortcut. That actually is the long cut. There are shorter cuts to make, but I would encourage you to be consistent in choosing a reference level and stick with it throughout the course of a problem. We're about to learn how to use that for a practice question, but this takes us up to all the things we talked about on Friday. Any questions before we go further from here? All right, we're going to talk about the scorpion a little bit because Friday was our day for Busch Gardens Physics Day, and we did not get to go, which makes me very sad. But someday we'll be out of this and we'll be able to go. So the thing about the scorpion that I like is that, and I talked about this on Fridays, you can see the entire thing from one vantage point. which means you can make pretty straightforward and consistent observations about what the ride is doing from different vantage points. We know that the chain lift is where energy is given to the ride. We talked about that on Friday. That work is done in lifting the cars to the top of the first hill. And that's the chain lift. So for today, we're going to say that you are riding the Scorpion, which means you, being 60 kilograms, are going to be lifted to the top of the first lift hill. You'll be taken to here. The lift hill is 30 meters above the ground. Do me a favor, calculate how much work was done by the chain lift in getting you to the top of the first hill. I'll pick on one of you in just a minute, but you may want your calculator for that. And I'm asking you a trick question. And so hopefully you'll see through the trick and do what I'm asking you to calculate, but that's what I want. I'm going to call on one of you in about 3 minutes. Calculate the amount of work done by the chain lift and getting you to the top of the first hill. Again, I'll call on one of you in just a minute. All right, that's enough time. First, you're not calculating work. You're calculating something else, I hope. So let's see. I'm going to be leaning into the people at home today for sure. So who's my favorite person to pick on at home? It's always one or two. All right, Fatima, can you help me out with this one?
Yes. Okay. I'm guessing that you would do
Can I give you a good starting point?
yeah.
All right. The chain lift lifted you up to the top of the first lift hill. When you get there, are you above the reference level?
Yes.
I think so too. I think the reference level was the ground. And I think you're now 30 meters above the reference level. So although I'm asking for work, I think what I'm really asking you to figure out is how much gravitational potential energy you have. Because that would represent how much work was done in getting you above the ground. So I'm going to go back to my definition of potential energy. Potential energy is work done against a conservative force. In this case, the work done against gravity. So we're going to use this function for gravitational potential energy, okay? So I only need to know 3 things. I need to know the mass of the object. What do we got there?
Is it 60 kilograms?
Yep, perfect. We're going to need to use something for the acceleration of gravity. I think we'll use 10. I like 10. It's nice and easy. And H minus H naught is going to represent how high you were lifted relative to your starting point. How high were you lifted relative to your starting point?
Is it 30?
Sure is. So there we go. This part, of course, the units work out to be Newton. This is Newton meters, so the whole thing will come out to be joules. So all you got to do is bang those together and tell me what it is.
18,000
That's
joules.
right. You have 18,000 joules of energy. So that's what we're going for. When we reach the top of that first lift hill, the work done by the chain lift was 18,000 joules of work. Notice the language that can be used here. Although we calculated the amount of gravitational potential energy that you have at the top of this hill, having the question ask you about work makes you think you need to know what this force is. Makes you think you need to know how far you went, but you don't. That's the way these problems are going to be. They're going to try and see if they can trick you. But when you reach the top of that first lift hill, you now have gravitational potential energy. So the work done on you has to be at least equal to the gravitational potential energy you have at the top of the first lift hill. I would encourage you to put something in your notes to that effect. That work done in lifting somebody results in a change in the potential energy. The work done in lifting somebody results in a change in the potential energy. So if you're suddenly higher than you were, you might not know what force did that. You might not know how far you traveled, but you're now higher, so you can calculate your new potential energy. Now, I'm going to kind of erase this a little bit so it doesn't take up so much space, and just put 18,000 right here. Now, once you have that energy, this energy stays with you throughout the course of the ride, unless something acts to take the energy away. This concept, this idea about energy is a way for us to study the play between forces without having to study forces themselves. Meaning the cart, you in this car, now have a certain amount of energy. That energy doesn't have to stay potential energy the whole time. Gravity can begin to pull you downwards, and as it does, it's going to speed you up. It's going to do work on you. At some point or another, you're going to make it to a point where you're 15 meters from the ground because gravity did work on you. At that moment, you're going to have gravitational potential energy because you're still above the reference level. But you're not going to have as much because you're not as high as you were before. That remaining energy only has one place to go. It's going to be transformed into kinetic. Gravity does work bringing you down. That work changes your kinetic energy. But if there's nothing to take the energy away, the total amount of energy you have here has to stay equal to the amount of energy you were given at the beginning. This is known as conservation of energy. And I'm going to put the word mechanical in here because we're looking at a subset of this rule. Conservation rules are very powerful in science. The word conservation means to stay the same. That's what it means. The problem with conservation rules is that they have to be applied correctly for them to be powerful and useful. What I mean by that is there's a difference between conservation of mechanical energy and conservation of energy. Conservation of mechanical energy means the mechanical energy of your system stays constant. We have talked only about two forms of mechanical energy now. Gravitational potential is one of them, and kinetic is the other. But what we're saying here is that if there's nothing to take the energy out of a system, the energy of the system stays the same. What this means for us is that we can study any place where the cars happen to be and know that at any of the places where the cars happen to be, the energy has to remain constant. Let's say that the loop has a radius of 10 meters. I would like you to tell me how fast the cars are going at the 15-meter mark and at the top of the first hill. I want you to use this concept of conservation to do so. And I'm going to give you a couple of pointers about how to do this. Conservation of energy means that I can compare one state of the problem with any other state of the problem that exists. I'm considering 3 separate states of the problem. If no energy is removed from the system, the energy at one state has to be equal to the energy at every other state. Which means I can set the energy at state 1 equal to the energy at state 2. I can set the energy at state 2 equal to the energy at state 3. I know how much energy I have at state 1, so I know the amount of energy I'm going to have at state 2 and state 3. When I look at individual states, I can deduce what types of energy probably exist at those states. For example, at state 2, am I above the reference level? If I'm above the reference level, which I chose at the beginning of the problem, then I likely have gravitational kinetic energy. Am I likely moving at that state? If I am, then I've probably got kinetic energy too. So at state 2, I should have a little bit of gravitational potential energy and a little bit of kinetic energy, but it all has to equal the amount of energy I had at state 1. Take a moment and see if you can't figure out how fast you're going at state 2 and how fast you're going at state 3. I want the in-class folks to do state 2, and I want the at-home folks to do state 3. Feel free to talk it out. You guys at home, I'm going to put you on mute so you can talk to each other but not be heard in the classroom. You guys in the classroom, be happy to talk it out at your tables with each other. And I'm going to call on a person at home and a person in the classroom in about 5 minutes.
All right, so where do we want to start with state 3?
We should probably set up the equation first and plug in any known variables.
Okay. So we're using the mg times height minus height naught plus 1/2 mv squared, right?
Yeah.
For the height, are we just using the radius times 2 for the, like, because he's at the top of the loop? So
Yeah.
on 20.
Yeah,
All right.
that would make sense. Did you guys end up getting 200 equals v squared?
Yes. Does he want us to,
You don't have to do it in the order we did it. You can do it any order you like.
want us to like square root that or just leave it
All
as
right, it's been about enough time. It's not a full 5 minutes, but I'm really not convinced it takes 5 minutes to do this. So you guys at home, give me just 1 second. Get you back. All right, so let's start with doing the velocity at state 2. So that's gonna be somebody in our classroom here. So I don't know who to pick. How about Adi? Adi says you got 17 meters per second. Can you tell me what you did to get that?
Well, I did 9,000 plus 150
Where'd you get the 10,000 from?
no, 9,000.
Well, where'd you get the 9,000 from?
Because there's it's 50 meters away, so it's half of the physical energy.
Okay, so he surmised that because we are half the height, that we only had half the amount of gravitational potential energy. That's a reasonable assumption. I mean, you can just do 60 times 10 times 15 as well. But yep, that's right. And then he did what with that?
I added that to half times, 1/2 times 60 times b squared, and then I just all 30.
Yeah, that's all I gotta do. All right, it's pretty straightforward, I hope. And then you got a velocity of 17 meters per second. Excellent. So let's see. Got to pick somebody at home. So how about Emma? Can you tell me what you did for state 3?
I got 14.1 as my final answer, and I found the height was 20 meters because you're the full diameter, so you'd be 20 meters. And
All right,
then,
I'm gonna stop you right there. That's the kind of silly stuff that they'll throw in there just to see if you're really paying attention. There are plenty of people who probably put 10 meters in there in first period because they didn't talk it out at all. They weren't really thinking. But yeah, when you're here, you're 20 meters above the reference level because you're a diameter above the reference level. So don't fall for tricks like that. They're gonna throw that on the test. I'm gonna throw it on the test. So when you did that was 12,000 joules of energy.
yes.
And what else did you do with that?
And then I plugged in the mass to find the kinetic, and I divided by 30, and I got v squared equals 200, and then v is just 14.14.
Excellent. So 14 meters per second, 17 meters per second. Give me a quick, this hard or is this easy? All right, so let's talk about a few things here that I am leaving out intentionally because I want to just kind of see this and practice this a little bit from the beginning. No, my head's in the way, but all I did was put 14 meters per second there. I think you guys can, oops, wrong way. There, you can figure that out. See, 14 meters per second. All right, so this is not what really happens. All right, this is playtime right here. Because although we're talking about this concept of conservation of energy, it's a nice concept, but is it very likely that in a real roller coaster, the energy just stays constant like this? It's probably not. There are lots of things out there that can take energy away from the system. So in a real roller coaster, there's probably things that are leaking energy off the system the whole time. Friction probably being the biggest one here. Friction is going to act to take energy out of the system. It's going to lower the total amount of energy the longer the system runs. And there's air resistance, and there's sound, and there's other things acting. It's not just always friction. In real circumstances, in real systems, there is likely work being done by other forces that you don't have control over. And those forces are taking energy out of the system. True conservation of mechanical energy requires that the system is not experiencing any forces except that of gravity or other conservative forces. We're only going to talk about 2 conservative forces in this unit. So if it's not a spring or it's not gravity, then it's taking energy away from the system. Worse, and those of you not writing that down probably should write this down, non-conservative forces are path dependent. They're path dependent. What that means is the longer your roller coaster track, the more energy you're going to lose to something like friction or air resistance, because they act as long as the object is moving. So if you want to make a really, really long roller coaster, you're going to have to take into account that you're going to lose more energy due to friction than a shorter roller coaster. So although we can use conservation of energy in kind of a hypothetical way, real things probably have less energy. How's that going to impact things like these velocities? Do you think it's going to make these velocities faster or slower? Yeah, because we're going to have less energy to actually work with. So there's absolutely no reason why I couldn't tell you that when you actually make it to state 3, you're only traveling 10 meters per second, and then ask you to tell me how much energy was lost due to friction. That's the kind of problem I'm very likely to ask on the test. So you need to know that when we say energy is conserved, we're only doing so for kind of a special case, a play case, like an ideal case. And that we're going to play with that a little bit and talk about the real case where energy is lost due to something like friction, which is why I'm going to ask you to do this for me. At state 3, we're actually only traveling 8 meters per second. How much work was done by friction? This question is for the people who I think are not paying real close attention. I'm going to hit you up. I'm not going to say if that's in the classroom or not, because I got people at home that just sprung to life because all of a sudden they heard a question mark. But I'll say it again. Let's say that when we actually make it to that point, at state 3, we only have a velocity of 8 meters per second. How much energy was taken away by friction? So I'll give you about 2 minutes. $60 seconds left. All right. 30 seconds left. Should be done with those calculators by now. Okay, Chloe, can you tell me what to do here?
I assume you'd have to add friction somewhere into the equation.
Perhaps. That's one way to think about it. Do me this favor for a minute, will you? Can you tell me how much kinetic energy we have when we're only traveling 8 meters per second?
1,920.
1,920. Did anybody else get that? All right, so that's how much energy I have when I'm traveling 8 meters per second. And we are still, right, 20 meters in the air. So we have 12,000 joules of potential energy, but only 1,920 joules of kinetic energy. Now, when you add those two things together, we get 13,920 joules of energy. Is this less than, equal to, or greater than 18,000 joules of energy? Right. So the work done by friction has to be what's missing here. It's the amount of energy that has disappeared from the system. All I have to do to figure it out is subtract it from the original amount I had. So I take my 18,000, I subtract 13,920. And that's going to tell me how many joules of energy was taken out of the system by friction. You said, do I have to add it? Yeah, you could add it right here. If you want this to balance, this is the amount of energy that was lost. And by subtracting the amount of energy we know about from the energy that we started with, this tells us what energy went into the environment. What heated up the track or whatever. Oh, I don't really care what the answer is. This is supposed to be just an opportunity for you to practice. This number of joules is the amount of energy we can't get back. And this is what I would expect you to be able to do. Understand the difference between the real and the ideal. So the ideal would say we'd be going 14 meters per second here. The real says, no, you lost some energy, so you're going less. Does that make sense, folks? Just easy enough? All right, we're gonna try one more thing and see if I can trick you. But then we're gonna be probably coming up on the end of the class period here, so. Let's say I have a little toy car. It's 1 kilogram, and I can launch it at 5 meters per second. And I have a ramp that will make that car go straight up into the air. If this is an ideal situation, what is the maximum height that the car reaches in the air? Give it a shot. What the maximum height the car reaches in the air. Don't be all day about this one. This one's pretty straightforward. Uh-oh. Time for the pledge. I want to be done. What kind of energy do you have when we launch the car? That's right. At state 1, we have kinetic energy only 1/2 times 1 times 5 squared. Now, if there's no losses to the environment, when you make it to your max height, do you have any kinetic energy? At any one of your states, you should ask yourself, what forms of energy are you likely to have? If you're above the reference level, you've got gravitational potential. That's going to be mgh minus h naught. If you're moving, you have kinetic. But at our maximum height, we shouldn't be moving. If we're moving at our maximum height, then A, we're probably not at our maximum height, or we're not going straight up or straight down. So I think the max height is going to be when we are not moving, which just leaves this as 1 times 10 times h max. That should have been all you had to do. So I don't know, how high is that? Sure. 1.2 meters. No, 2.5. 2.5 meters. All right, folks, that's all for today. Please get started on your homework. It is all achievable. We have almost all the information you need to do your homework. We're just going to be practicing the next couple of days, and we're going to do a demo tomorrow. So have a great day. I'll see all of y'all tomorrow. Any questions from you folks at home? All right, folks, see you later.
Bye, Mr. Shelton.
Bye-bye.